4 light-years. It sounds almost closer neighbour in the cosmic map, yet for us it may as well be forever. Alpha Centauri lies just beyond the faint blur of southern stars, the nearest stellar system home to suns that resemble our own. In human terms, it is the next town over. In cosmic reality, it is an ocean so wide that light itself must sail for more than 4 years to cross it. Every telescope that points toward it sees not the present, but light that left before smartphones, before the internet, before some of us were even born. We have built machines that circle planets, that skim the edges of the solar wind, that whisper through the void. Voyager 1 has travelled for nearly half a century, a marvel of human persistence, and yet it has crossed only a fraction of 1% of the distance to Alpha Centauri. Our fastest rockets move at 17 kilometers per second, but even at that pace the journey would take over 75,000 years. What looks nearby on a star map is in truth a mirage shaped by scales our minds were never built to handle. When astronomers first realized how far even the nearest star truly is, the numbers broke something ancient in us. The quiet belief that the universe is reachable. We could see the light of another sun, but we could never touch it. Every time I look at Alpha Centauri shimmering faintly above the horizon, I feel the distance as a weight invisible, patient absolute. It reminds me that the sky's beauty hides its cruelty. What we can see we may never hold. Launched in 1977, Voyager 1 was never meant to last this long. It was built for a short journey through the outer planets, a final glance at Jupiter, Saturn and beyond before fading quietly into the cold. Yet nearly half a century later it is still moving, still transmitting faint signals across the emptiness. Each whisper it sends takes more than 22 hours to reach Earth, crossing a gulf of space so large that sunlight there is only a pale echo of what we know. Out there beyond the orbit of Pluto, Voyager drifts through the interstellar medium, a place where atoms are so scarce that a cubic meter of space might contain only a handful. Its golden record spins in silence, carrying the sounds of rain birds' laughter and human voices preserved like fossils inside a machine of fading power. Every second, the probe moves 17 kilometers farther away, slipping deeper into a darkness that grows thicker with distance and time. If it keeps going, Voyager will need more than 75,000 years to reach Alpha Centauri. By then our cities will be dust, our languages gone, and even our sun may have changed its glow. Yet the probe will still glide on a tiny piece of human defiance cutting through the void, a silent witness to what curiosity once dared to launch. Sometimes when I think about Voyager, I imagine it not as a machine but as a message, a lone thought drifting between stars, too slow to arrive yet too brave to stop. When we talk about Alpha Centauri, we often call it the nearest star. The phrase sounds comforting, like something within reach, a destination only waiting for the right ship. But the word nearest in astronomy doesn't mean what it means on Earth. On the cosmic stage, close can still mean impossibly far. To grasp that distance, imagine shrinking the entire solar system from the Sun to Neptune down to the size of a coin. On that scale, Alpha Centauri would still be another coin placed more than 100 meters away. Between them stretches nothing. No planets, no gas, not even dust thick enough to see. Just a darkness so vast that the human brain refuses to hold it. The light that leaves Alpha Centauri tonight will not reach us until the year 2029. It's already on its way, invisible, indifferent, crossing the void at the ultimate speed allowed by nature. Every beam is a messenger of the past, showing us a moment that no longer exists. We don't see Alpha Centauri as it is. We see it as it was. That's what makes the universe deceptive. Its beauty feels close enough to touch, but the truth hides behind time itself. What our eyes see is always a memory. The sky is not a window, but a history book written in light. Light is the fastest thing that exists, the universe's ultimate messenger. It races through the void at almost 300,000 kilometers every second, a speed so immense it defies imagination. And yet even at that velocity it takes more than 4 years to cross the narrow gulf between us and Alpha Centauri. 4 years for light and for anything slower an eternity. When we look at the stars, we're not seeing space, we're seeing time. The light that reaches us tonight left its home long before our world looked the way it does now. From Alpha Centauri, it began its journey when humans were still figuring out how to send signals to satellites. From the Andromeda Galaxy, that light began when our ancestors first stood upright. The farther we look, the older everything becomes. This delay is not just a poetic idea, it's a law of physics. The speed of light doesn't only limit travel, it limits knowledge itself. We can never see the universe as it is, only as it was. The cosmos hides its present behind an unbreakable curtain of time, and that's the cruel beauty of it. The closer we come to understanding the stars, the more we realize how completely we're trapped by their light. Before telescopes, the night sky was our first mystery, a canvas of unreachable fires. We drew constellations to tame the chaos, to give the stars names and stories to pretend we understood them. But when we finally began to measure the heavens, the truth erased every myth we had written. The distances were too large, the emptiness too complete. Our first maps of nearby stars looked simple dots and lines sketched across black paper, but those lines were lies of comfort. The dots weren't neighbours, they were islands separated by light years of nothing. Each one burned alone, surrounded by a silence so vast it defied geometry. To chart the universe was to admit our insignificance, to learn that every line we drew was a bridge that could never be crossed. Astronomers tried to imagine the journey, how long it would take to move from one star to another. Even the nearest destination, Alpha Centauri, demanded timescales beyond civilization itself. Empires could rise and fall before a single ship arrived. The idea of interstellar travel wasn't inspiring. It was devastating. And yet humanity kept drawing those maps. We couldn't stop, because even if they led nowhere, they reminded us that nowhere was still part of the universe, and that somehow, so were we. Alpha Centauri feels close because we can name it. We can point to it on a map, see it shimmer in the southern sky, and even imagine a spacecraft sailing there one day. But that illusion of nearness is what makes the truth harder to bear. In the scale of the cosmos, proximity is not measured in kilometers. It's measured in the failure of time itself to bridge the gap. Light can cross that distance in a few short years, but light has no mass, no hunger, no memory. For us, every gram of matter is a burden. Every heartbeat adds weight. To reach another star, we must carry not just fuel and metal, but everything that makes us human. Oxygen, food, protection, meaning, and those things slow us down far more than gravity ever could. The paradox is cruel. The closer a star appears, the more impossible it becomes. The distances that define space are not there to keep us away. They are what allow the universe to exist at all. If the stars were truly close, their gravity would tear each other apart. Separation is not an accident, it's the reason the night sky shines instead of burns. We dream of crossing that distance, but maybe the dream itself is the point. The unreachable horizon gives meaning to motion. Without it, even light would have nowhere left to go. Every measurement in space begins as a betrayal of intuition. Our minds evolved to understand rivers and mountains, not light years. We can picture 1 million, maybe 1 billion, but the numbers of astronomy live far beyond imagination. A light year is nearly 10 trillion kilometers a unit, so immense that writing it down does nothing to make it real. Scale in the cosmic sense is not just distance. It's a law that governs everything: the brightness of stars, the speed of orbits, the very shape of time. The same physics that keeps the moon circling Earth also keeps galaxies turning, yet across magnitudes of size that make comprehension collapse. We stand on one grain of dust trying to describe an ocean that has no shore. When we say Alpha Centauri is only 4 light years away, we forget that those 4 light years contain more emptiness than any desert we've ever known. Between our sun and that star lies nothing we can touch or name, nothing to slow us down or speed us up, just a void so vast that even numbers start to lose meaning. Sometimes when I think about scale, I realize that the universe is not large because it wants to intimidate us. It's large because it can be, and because somewhere within that immensity, smallness is what makes us aware. Every night the stars rise like promises we can never collect. They burn with such clarity that our ancestors once believed they were holes in the sky, windows to heaven, not unreachable suns. But even now, knowing what they are, that old illusion still lingers. The stars look close because light deceives us. It travels in straight lines, hiding the centuries it carries within each photon. The human eye turns distance into beauty. It compresses the scale of the cosmos into something gentle enough to bear. Yet beneath that calm shimmer lies an impossible truth. The light we see tonight left its home before modern civilization existed. The stars we admire may already be gone, their deaths hidden by the long delay of their light. To see the stars is to touch the past, not the present. The universe shows us memories, never reality. Every night, sky is an archive of ghosts. Suns that burned planets that turned lives that might have looked back toward us. We stare upward and feel connection. What we reach for has already vanished. And maybe that's why we keep looking. The light that can never be touched is also what keeps us from forgetting that we exist. At first, numbers were our way of understanding the stars. We measured their distance, brightness, and speed, believing that with enough calculation the universe would make sense. But the more we counted, the less human those numbers became. Millions turned to billions, billions to trillions, until language itself started to fail. When we say a spacecraft would need 75,000 years to reach the nearest star, the words leave our mouths easily. Yet if we tried to feel that span, we couldn't. 75,000 years ago, humanity hadn't even invented writing. The glaciers still covered half the world, and the constellations we know today didn't yet exist. By the time Voyager crosses that distance, continents will have shifted, and our descendants, if they survive, will be something else entirely. Numbers reveal, but they also numb. They allow us to speak of the infinite without collapsing beneath it. We can calculate the age of the universe, but not what it means. We can measure the distance to Alpha Centauri, but not the loneliness that distance implies. Perhaps that's the final trick of the cosmos. It lets us understand just enough to feel small, but never enough to escape the feeling. If we launched a ship toward Alpha Centauri tonight, travelling at the speed of Voyager 1, it would arrive long after every trace of our civilization had turned to dust. Languages would evolve, continents drift, and even the memory of Earth's nations would fade before that tiny probe reached another sun. Its arrival wouldn't be a triumph, it would be an echo from an age long vanished. Interstellar travel isn't a race through space, it's a dialogue with time. Each kilometre forward is also 1,000 years deeper into the future. Even a vessel moving at 1% of light speed, an engineering miracle, would still take 4 centuries to arrive. Generations would live and die aboard it, never knowing if their descendants would see the destination. And yet we still dream of the journey. Because to move toward another star, no matter how slowly, is to defy the silence that surrounds us. The universe measures distance in patience, and the act of beginning, no matter how futile, becomes its own kind of arrival. To reach another world, we must first escape our own. That sounds simple until you realize how deep the sun's gravity well truly is. Every planet, every grain of dust in our solar system orbits within its invisible pull, bound by a force that has ruled for more than 4 billion years. Earth's escape velocity is 11 kilometers per second, but to break free from the sun entirely, a spacecraft must reach 42. Voyager managed it only by stealing speed from the giant planets, a cosmic slingshot using Jupiter's immense gravity. Even then it crawls outward at a pace that feels like stillness. It is free, yes, but only just. The sun's grasp stretches for billions of kilometers, its influence reaching far beyond the last frozen comets at the edge of the heliosphere. When I imagine this, I no longer see the sun as just our life-giver. It's also our jailer holding us close even as we dream of leaving. To reach another star, we must first pay the toll of our own, and that price for now remains far beyond what we can afford. Every rocket begins as a promise to lift us beyond Earth's pull, to defy the weight of our own world. But in the quiet language of physics, that promise quickly turns cruel. The faster you want to go, the more fuel you need. The more fuel you add, the heavier your rocket becomes, and the heavier it gets, the more fuel it needs just to lift the fuel it already carries. It's a loop with no mercy. Chemical propulsion, the fire that carried us to the moon, burns bright, but its efficiency is laughable on a cosmic scale. Even our best hydrogen-oxygen engines, the ones that scream through the night on pillars of flame, can only push a spacecraft to about 17 kilometers per second. That's enough to cross the solar system, but to reach even 1% of light speed we would need to go 10,000 times faster. If we tried to do that with chemical fuel, we'd need more propellant than there are atoms in the observable universe. The math doesn't just say difficult, it says impossible. The stars demand a different kind of fire, not one born of combustion, but of fusion, of annihilation, or of light itself. Until we learn to wield those powers, every rocket that leaves Earth remains just a spark against eternity. For more than half a century, we've launched our hopes on columns of flame. Apollo Voyager, Artemis, all born from the same chemistry, the same violent beauty of controlled explosions. A rocket launch feels limitless when you watch it. The Earth trembling beneath a storm of sound. Yet even at its peak, that power fades almost immediately. Within minutes, the engines fall silent and the vastness swallows the roar. A chemical rocket is magnificent within the neighborhood of planets, but pitiful when measured against the scale of stars. It burns fast, dies fast, and carries nothing close to the energy we need. Even if we filled Earth itself with propellant, the reach of that flame would end long before Alpha Centauri's light ever touched the hull. Sometimes I think of those old rockets as humanity's first heartbeat. Brief, fiery, and full of hope. They taught us how to rise, but not how to endure. To travel farther, we'll need a new language of motion. One written not in fire and smoke, but in light, fusion, and fields we have yet to discover. To leave Earth is difficult. To leave the Sun is almost impossible. Our star's gravity is not a chain we can see, but it binds every world in its reach, curving their paths into endless circles. Even at the edge of the solar system, billions of kilometers away, its pull persists faint but never gone. A spacecraft must climb out of this invisible ocean layer by layer. First, it escapes Earth's gravity, clawing skyward at 11 kilometers per second. Then it must overcome the orbital speed of our planet itself, 30 kilometers per second around the Sun. Only when it exceeds 42 can it finally drift free unanchored into the interstellar dark. Voyager 1 is the only human creation to have done this. After nearly half a century, it still moves outward farther than any object we've ever built, yet it has covered less than 1% of the distance to the nearest star. It will wander for billions of years, still tethered faintly to the Sun's memory. The farther it drifts, the more it reminds us. The same star that gives us life also demands tribute for every attempt to leave. Every launch begins with escape not from danger, but from comfort. To break free of Earth's gravity, we must burn almost all the energy we have just to reach orbit. For a rocket, the first few hundred kilometers are the hardest it will ever travel. Nearly all its fuel is spent before it even touches space. But orbit is not freedom. Earth itself is still falling endlessly around the Sun, locked in a golden loop of motion at 30 kilometers per second. To go farther, to leave the Sun's kingdom entirely, we must pay again. It's a cruel hierarchy of energy. Every step away from home costs exponentially more than the last. Even the most powerful engines we can imagine must first climb this invisible ladder. Nuclear fusion or antimatter, they all begin by fighting the pull that made us. The universe hides its frontiers behind the gravity wells of stars, and ours, though beautiful, is steep. The Sun nurtures us, but it also holds us close, as if it knows that every journey worth taking begins with the pain of letting go. Every journey has a boundary, a point beyond which motion itself begins to break. For the universe, that boundary is the speed of light. 300,000 kilometers every second, not just a record, but a rule. It isn't a number carved in stone. It's written into the fabric of reality itself. Every photon, every radio wave, every sunrise obeys it without exception. Einstein didn't invent this limit, he revealed it. In his equations, space and time became two sides of the same thing fused into a single geometry, where motion through one distorts the other. The faster you move, the slower time flows for you. The heavier you become, the more the universe resists your push forward. As you approach light speed, resistance becomes infinite. So does the energy you'd need to go faster. That's why nothing with mass can ever reach it. To move like light, you must be light stripped of weight memory and everything that defines existence. The limit isn't just physical, it's philosophical. It's the line between being and not being, between the possible and the radiant ghosts that pass us at light speed, carrying the universe's messages while we remain forever behind. When Einstein described the speed of light as a constant, he didn't mean it was merely fast. He meant it was foundational, the speed that defines reality itself. Everything that exists, from the orbit of planets to the ticking of your heartbeat, happens within the limits that light allows. It's not just a ceiling, it's the structure of time and causality. Imagine chasing a beam of light. No matter how fast you run, it always moves away from you at the same speed. Time bends to make that true. As you accelerate seconds, for you stretch, longer distances shrink and the universe reshapes itself to protect the rule. This is not a suggestion the cosmos negotiates with, it's a covenant written into space-time. In that simple truth lies something humbling. The faster we go, the slower we exist. Push hard enough, and time itself begins to dissolve beneath us. The universe allows motion, but only by taxing the one thing we can never replace: our moments. To reach the stars, we must first spend time, and at light speed we would spend all of it. In Einstein's world, energy and mass are not opposites. They are mirrors. Add enough energy to something and it becomes heavier. Push it faster and it demands still more. The closer it moves toward light speed, the more its own motion turns against it, bending the universe to hold it back. This isn't friction or air resistance. It's the geometry of space-time itself saying no. Every gram of matter carries an unimaginable store of energy bound within its existence by the equation E = mc2. But the same equation that reveals this power also reveals the trap. To push even a small object near the speed of light would require more energy than all the stars in our galaxy could provide. In the math of the cosmos, the faster you go, the more impossible the next step becomes. And yet this limit gives the universe its order. Without it, cause and effect would collapse. Time would lose its direction. Light speed isn't a wall built to confine us. It's the scaffold that keeps reality upright. It's the reason we can measure, predict, and trust the flow of moments at all. The barrier that stops us from reaching the stars is the same one that keeps the stars from falling into chaos. Imagine pushing harder and harder, feeling the universe resist you with every heartbeat. As your speed grows, so does your mass, not the matter you carry, but the energy that gravity and motion weave around you. Near light speed, this effect becomes overwhelming. Your momentum warps space-time itself, demanding infinite energy just to move a little faster. The closer you get, the heavier you become until your own motion begins to bend the world around you. This is the wall that ends every dream of superluminal travel. Rockets, particles, even beams of plasma all crash against the same equation. You can approach light speed but never touch it, because touching it would make you infinite, and infinity cannot exist inside a finite universe. It's a haunting symmetry. The universe allows acceleration but forbids arrival. The faster you go, the slower your time flows. Push too far and eternity gathers around you like armor. To go faster than light would not just break physics, it would break meaning itself. As speed climbs, time begins to twist. To a stationary observer, a fast-moving traveller seems to slow down their heartbeat, stretching into the rhythm of the universe itself. Seconds for them become minutes for us, minutes become years. From their view, though, nothing feels different. The clock on their ship ticks. Normally, the stars drift quietly past. But when they look back toward home, everything has changed. This is time dilation, one of relativity's strangest gifts. A traveller nearing light speed could cross vast distances in what feels like a short journey, yet return to find centuries gone. Entire civilizations could rise and fall while they experienced only a few years. In chasing the stars, they would outrun history but lose the world they left behind. If such a voyage were ever possible, the traveller would become a ghost alive but displaced, moving through a slower universe. To them, time would stretch like silk. To us, they'd vanish into myth. And perhaps that's the true limit of light speed. Not a wall of energy, but a horizon of loneliness where time itself decides what cannot follow. Space isn't empty, it's a sea of geometry. Every particle, every ray of light, every breath of radiation moves across a fabric that can stretch, curve, and ripple. Einstein called it space-time, not two things joined together, but one vast ocean, where distance and duration flow as a single current. We float inside it, carried by its invisible tides. When a massive object appears, a star, a planet, a black hole, it bends this ocean. The path that light takes, the rhythm of time itself, curves around that weight. What we feel as gravity is only the experience of moving through that curvature like boats following the slope of a wave. The faster we move through space, the slower we drift through time. At first it sounds abstract until you realize we live inside that distortion every second. Our clocks tick differently on mountaintops than at sea level. GPS satellites must correct for relativity just to tell you where you are. Even standing still, we're riding the currents of space-time forever, moving through an ocean that has no shore and no calm. If we could chase a beam of light, what would we see? Einstein once asked himself that question as a teenager, and the answer reshaped the universe. No matter how fast you run, light never slows down, it always escapes ahead, moving through space at the same perfect speed. To preserve that truth, time itself must bend. As you accelerate, every heartbeat stretches, every second becomes longer. The world around you blurs, distances shorten, and colours shift toward the blue. The faster you go, the more the universe rearranges itself to keep light untouchable. Motion doesn't just change position, it changes existence. From your perspective, the journey feels normal. Time passes as it always has. But to everyone watching from afar, you've begun to dissolve into the slow rhythm of cosmic time. The faster you chase light, the more it turns into a mirror showing you what you can never become. Somewhere between motion and stillness, you stop being a traveller and start becoming a shadow cast by time itself. Everything we know about the universe comes from light. We have never touched a star, never crossed the gulf between galaxies, yet we can describe their temperature, age, and motion with astonishing precision. Every photon that reaches us is a messenger carrying the memory of where it came from. The cosmos speaks in light, and we have learned to listen. When a telescope captures a distant galaxy, it isn't seeing the present. It's collecting ancient signals waves that left billions of years ago, long before Earth existed. Those photons have crossed an expanding universe stretched and reddened by time itself. By measuring their faint arrival, we rebuild the story of everything. How stars were born, how they died, and how their ashes became us. Photons are not just illumination, they are the fabric of history. Without them, space would be silent and unknowable. Every colour in the night sky is an echo of something that once burned. We're not just looking into space when we gaze at the stars. We're looking into time, reading a message written in light by hands that no longer exist. No matter how far we build our telescopes, there is a limit to what we can see. Beyond a certain distance, light has not had enough time to reach us since the universe began. That invisible boundary is called the cosmic horizon, the edge of the observable universe. It isn't a wall made of matter or energy. It's a horizon made of time. Every year, as the universe expands, new regions slip beyond that horizon forever. Galaxies that once shone in our telescopes fade into redder and redder light until they vanish completely. Their photons can no longer outrun the stretching of space itself. What lies beyond them still exists, but it has become unreachable, not just to us but to physics itself. It's strange to think that the universe has parts we can never witness, not because they're hidden, but because reality doesn't allow the message to arrive. The horizon defines the ultimate boundary of knowledge, the line between the known and the unknowable. We live inside that boundary like fish in a glowing sphere surrounded by the light of all that we will ever see. Human imagination has never accepted limits easily. The moment Einstein drew the line at light speed, we began searching for cracks in it. Could we tunnel through space, fold it, twist it, or ride on something that moved faster than light itself? From warp drives to tachyons, the ideas filled books and films, each promising to outwit the universe's oldest rule. But the math is merciless. Anything faster than light would reverse cause and effect. Events could happen before their causes. Messages could arrive before they were sent. Reality would unravel and time would lose direction. Physics protects itself by making such motion impossible. Particles with mass can only approach the limit, never cross it. Those without mass can only live at the limit, never slow below it. The dream of outrunning light isn't foolish, it's human. It's what drives science forward even when the answer is no. Each failure teaches us more about the structure we inhabit. The universe doesn't punish curiosity. It just insists we play by its rules. And in that refusal there's something oddly comforting. The cosmos is consistent even in the face of our wildest dreams. For all our genius, we still ride to space on controlled explosions. Inside a chemical rocket, propellants burn in a fury of heat and pressure, hurling metal skyward at impossible acceleration. It's a spectacle of noise and fire, and yet by cosmic standards it's barely a flicker. The flame lasts only minutes. The push fades almost instantly, and the rocket begins to drift like ash in the wind. Chemical propulsion is a dead end for the stars. Its energy density, the power stored in every drop of fuel, is too small, too fleeting. We use it because it's the only thing we truly understand, the one technology that can claw us free from Earth's gravity. But beyond that, it has nothing left to give. To reach another star, a chemical rocket would need more fuel than atoms in the Milky Way. Still, every launch is a reminder of something beautiful. Even knowing the math, we like the engines anyway. We rise a little higher for a little while, chasing a dream the physics won't allow, and for a brief burning moment we touch the sky. When fire proved too heavy for the stars, we turn to electricity. Ion engines don't roar like rockets, they whisper. Inside their metallic chambers, atoms are stripped of electrons, turned into charged ions, and flung out the back at immense speed. Each particle carries only a tiny push, but over months and years those whispers add up to something extraordinary. Unlike chemical rockets that burn out in minutes, ion drives can stay alive for decades. They trade brute force for patience, pushing spacecraft with the delicate persistence of light on glass. Missions like Dawn and Deep Space One showed how far quiet endurance could take us, spiraling through the asteroid belt on streams of invisible power. But even the calm elegance of ion propulsion cannot escape the tyranny of energy. It's efficient, not powerful. The thrust is so weak that a sheet of paper could resist it. And though the engine may burn for years, it still crawls through a cosmos measured in light years. The whisper can carry us across planets, but not yet between the stars. In the cold years of the 20th century, when imagination still outran caution, scientists dreamed of starships driven by nuclear fire. The idea was simple and terrifying. Drop atomic bombs behind a massive shield and ride the shockwaves forward. Each detonation would hurl the ship a little faster, stacking thunder upon thunder until it reached a fraction of light speed. They called it Project Orion, a vessel of steel plates and physics where warheads replaced engines. In theory, it could have worked. A few thousand explosions, carefully timed, could fling a ship to the edge of interstellar space within a human lifetime. But the world turned away. Treaties banned nuclear detonations in space, and the dream fell silent under its own weight. Still, Orion remains one of the boldest concepts humanity ever conceived, a reminder that our ambition often walks the edge of madness. To ride a storm of bombs through the void was more than engineering. It was myth disguised as math. And though we never built it, the thought alone reveals how far we're willing to go when the stars begin to whisper our name. If chemical fire was too weak and nuclear bombs too violent, Perhaps the answer lay in the heart of the stars themselves. Fusion, the process that powers every sun, promised limitless energy. Two atoms of hydrogen colliding to form helium, releasing a burst of light that could drive ships for centuries. For decades, scientists dreamed of building a miniature star inside an engine, a flame that never burned out. On paper, it was perfect. A fusion drive could reach 10% of light speed fast enough to cross the Gulf to Alpha Centauri in less than a lifetime. No warheads, no waste, just the same reaction that warms every sunrise. But equations are patient and reality is cruel. To contain a star, you need temperatures of millions of degrees, magnetic fields that bend like gods, and materials that don't yet exist. Even today, fusion reactors on Earth are still learning to hold their fire. They flicker for seconds, then collapse back into silence. We are close, but not close enough. The dream of riding a sun remains frozen inside physics papers, a promise of light waiting for a civilization that has learned how to hold a star without being consumed by it. If fusion is the fire of the stars, antimatter is the fire of the universe itself. When a particle meets its mirror opposite, both vanish in a burst of pure energy, no smoke, no waste, just light. It is the most efficient fuel imaginable. A few grams could power a ship for years, perhaps even drive it to a significant fraction of light speed. For a moment, it seemed like the final key to interstellar flight. But nature hides it well. Antimatter doesn't exist freely. It must be made atom by atom in powerful accelerators, each particle costing more energy to create than it could ever release. Storing it is even harder. Touch normal matter, even the walls of its own container, and it detonates instantly. To hold it safely would require electromagnetic traps so perfect that a single failure could erase the ship in light. Still, the dream persists. Antimatter engines haunt the edge of science fiction and theory, where imagination dares to write equations faster than technology can follow. It is the ultimate paradox, a propulsion system that could carry us to the stars, powered by the very process that destroys everything it touches. Every dream of interstellar travel breaks on the same equation, the Tsiolkovsky rocket law. It looks harmless on paper. A simple relationship between fuel mass and velocity, but hidden inside is a curse. The faster you wish to go, the more fuel you must carry. The more fuel you carry, the heavier your ship becomes. And the heavier it gets, the more fuel it needs to move at all. This spiral has no mercy. It's the reason our rockets grow enormous just to lift a small payload, and why the stars stay far beyond reach. A craft trying to reach even 1% of light speed would need more fuel than could ever fit inside the universe itself. It's a paradox of ambition. The harder we try to escape gravity, the more it drags us back. In that cruel symmetry lies a lesson. The universe doesn't stop us with walls or weapons. It stops us with math, silent, flawless, and absolute. For all our ingenuity, every rocket we build carries within it the proof of its own limitations. The equation that reminds us that speed is not free and escape is never simple. Even if we could somehow build a ship fast enough to reach the stars, the universe would turn against us in another way. Space is not empty. Every cubic meter contains stray atoms, dust grains, and fragments of rock drifting in silence. At ordinary speeds, they are harmless. But at 1/10 of light speed, a single speck of dust hits like a bomb. A particle no larger than a grain of sand would strike with the energy of several kilograms of TNT. The hull would blister, vaporize, or simply disintegrate. A ship racing between the stars would face an endless storm of invisible bullets, each one capable of tearing it apart. Shielding could help thick layers of metal magnetic fields, clouds of plasma. But every layer adds weight, and weight is the enemy of speed. The faster we move, the more lethal space becomes. What looks like emptiness turns into a minefield of matter. Even light itself becomes a hazard, each photon smashing into the hull with increasing violence as energy climbs with speed. The void may look peaceful from afar, but at near relativistic velocity it is a sea of knives waiting in the dark. Beyond the safety of Earth's magnetic cocoon space is drenched in radiation. High-energy particles stream constantly from the sun, and from distant supernovae moving so fast they can pierce solid metal. Astronauts who spend too long outside Earth's protection watch tiny flashes of light dance behind their closed eyes, cosmic rays striking their retinas one by one. Now imagine travelling near light speed. Every particle ahead of you would slam into the hull with energies multiplied by relativity, transforming ordinary radiation into a torrent of destruction. Electronics would fry, atoms in your body would shatter. Even if you could surround the ship with layers of lead or magnetic fields, the particles would eventually tunnel through, poisoning everything inside. Radiation is the quiet predator of spaceflight, invisible, constant, and patient. It doesn't announce itself with noise or fire, only with decay. On the journey to another star, it would become the traveller's eternal companion, eroding both machine and mind until nothing remained but silence drifting through the dark. In the soft darkness between stars, countless grains of cosmic dust drift like snow, tiny fragments of ancient planets and dead suns. They seem harmless, suspended in the eternal calm of the void. But to a ship racing at even a fraction of light speed, those grains become bullets, each carrying the energy of high explosives. A single impact could vaporize a section of hull, releasing a plume of plasma that tears through the vessel like fire underwater. Thousands of such collisions over years of travel would shred any structure we know how to build. Engineers have imagined elaborate defenses, magnetic shields, plasma veils, even walls of sacrificial ice that absorb each strike. Yet every solution adds weight, complexity, and failure points. The interstellar void is not empty. It's a battlefield of inertia and chance. Between every star lies a thin haze of debris that punishes motion itself. The faster we move, the deadlier it becomes. In the end, it's not distance that kills the dream of travel, but the sheer hostility of the space between. To survive the storm of radiation and dust, a starship would need armor. Thick, dense, unyielding. But protection has a price. Every layer of shielding adds weight, and every kilogram of weight demands more energy to move. The safer the ship becomes, the slower it must travel. In trying to survive the journey, we make it impossible to complete. Engineers have proposed exotic solutions: electromagnetic bubbles that deflect charged particles, plasma fields that vaporize dust before impact, even artificial magnetic magnetospheres, mimicking Earth's own. Yet each of these requires immense power that itself produces radiation and heat that must be contained. The ship becomes a paradox, a fortress against space that is destroyed by its own defenses. In the end, the simplest answer may be surrender. Instead of fighting the universe, perhaps we drift with it, small, patient, protected only by time and distance. Because every layer of armor reminds us that survival in space isn't about strength. It's about humility before a universe that doesn't care whether we arrive. Deep space is soaked in the ghosts of dying stars. High-energy particles from supernovae and black hole jets race across the galaxy, each carrying the power to slice through atoms and DNA. On Earth, our atmosphere and magnetic field shield us from nearly all of it. But in interstellar space, there's no such protection, only the thin hull of a ship and the fragile walls of human cells. A single cosmic ray can pass straight through a body, breaking molecular bonds as it goes. One particle might do nothing, but billions over years would turn the traveller's biology into a slow-motion catastrophe. Cancer organ failure, neural decay. The symptoms would bloom long before the ship reached even a fraction of its destination. Some imagine surrounding the crew in water or liquid hydrogen materials that can absorb radiation. Others suggest letting machines travel in our place, metal bodies immune to the storm. But if the human form cannot survive the void between stars, then the question becomes darker. What exactly would arrive on the other side? We call it emptiness, but space is never truly empty. Even in the quietest corners of the galaxy, the vacuum hums with stray atoms, photons, and ghostly fields. Quantum mechanics tells us that particles flicker in and out of existence constantly. A restless energy that never goes still. It's this invisible turbulence that makes perfect vacuum impossible. For a ship travelling between stars, that ghostly presence becomes friction. Each passing atom, each wandering ion transfers momentum, heat and radiation. The faster you go, the more the vacuum pushes back, turning nothingness into resistance. It's like trying to sprint through air that you can't see but always feel pressing against you. Even the fabric of space-time itself isn't perfectly smooth. It fluctuates, vibrates and expands. On scales, that vast emptiness becomes an ocean subtle yet endlessly deep. In the end, the void is not our ally. It's alive in its own quiet way, reminding us that there is no such thing as nothing, and that even nothingness refuses to let us pass without a cost. Science fiction often imagines an elegant solution. If the stars are too far, let us simply sleep through the distance. Cryosleep, the dream of freezing time itself. A crew placed in suspended animation, their bodies pause between heartbeats. Their minds preserved in stillness until arrival. It feels simple, almost merciful, but biology is not designed to wait that long. Freezing living tissue shatters its cells. Thawing brings chaos as ice crystals tear through membranes and DNA. Even if we could cool the human body perfectly, metabolism would still collapse once energy stops flowing. Life is motion, and motion cannot be paused without a price. The same physics that traps us at sublight speed also anchors our biology to time's arrow. Researchers study deep-sea creatures, tardigrades and Arctic frogs, beings that endure suspended life for months, even years. Yet scaling that miracle to centuries in deep space under radiation and isolation remains far beyond reach. Cryosleep is beautiful because it promises escape, but like every dream born from distance, it fades when touched by reality. Even if we solved propulsion, shielding and biology, one barrier would remain: the mind. Space is not just vast, it is silent. A silence so complete it erases time. For years or decades, a crew would live in an unchanging environment, seeing the same walls, the same stars, the same darkness. There is no sunrise in interstellar space. No cycle of days to remind you that life still moves forward. Isolation bends perception. Without new experiences, thought loops back on itself. Boredom becomes anxiety. Anxiety turns to despair. Astronauts on the International Space Station already feel its edge after months in orbit, and they are still within sight of Earth. Multiply that isolation by 1,000 and even the strongest mind begins to fracture. Machines don't suffer loneliness, but humans are built for connection, for change, for the rhythm of living worlds. To sail through centuries of darkness would mean becoming something less human or more machine. The real void isn't outside the ship, it's the one that slowly opens inside those who dare to cross it. When nothing changes, time stops meaning anything. In the endless dark between stars, a year becomes indistinguishable from a decade. The clocks may still tick, but without sunrise or motion, those numbers lose their weight. A traveller drifting for generations would experience time not as progress, but as suspension, a slow erasure of purpose. Psychologists call it sensory monotony, but in space it becomes something deeper, temporal decay. Without new memories to anchor them, moments blur together until the mind forgets how to measure its own existence. A second feels like an hour, then an hour like a lifetime. The mind begins to fold inward, searching for boundaries in a place where none exist. Maybe that's why we cling so fiercely to stories of arrival. They remind us that time can still move forward, that not every journey must dissolve into stillness. In the dark ocean between the stars, hope itself becomes the only clock that still works. If speed is impossible, then perhaps time is the answer. Instead of racing toward another star, we could simply drift a self-contained world, carrying generations of travelers who would live, die, and be replaced before arrival. The so-called generation ship, a moving civilization, its journey measured not in years but in bloodlines. At first it sounds noble, a slow triumph of endurance. But history shows how fragile continuity can be. Languages shift, stories erode, meaning dissolves. After centuries adrift, would the passengers still remember why they left? Would Earth become a myth? a half-believed origin whispered to children who have never seen a sunrise. Such a vessel would be both ark and tomb, preserving humanity while erasing the humans who began the voyage. The ship would arrive, but the dream that launched it might not. In the end, the question isn't whether we could build a generation ship. It's whether the people who step off it would still call themselves us. A generation ship would have to be more than a vessel. It would be an ecosystem, a city, a world. Every drop of water recycled, every breath shared, every crop grown under artificial suns. Machines would replace seasons, algorithms would become weather. For centuries, nothing could fail. One broken system, one miscalculation, and the chain of survival would unravel. The challenge isn't just engineering, it's culture. How do you keep a society stable when its people will never see the destination? How do you sustain purpose when progress is invisible? Religion might return, or ritual or myth, shaping a new identity around endurance rather than discovery. The ship would no longer be travelling to a star, but within itself, generation after generation, orbiting a memory of Earth that fades a little more each century. Perhaps that's the real difficulty of interstellar travel. Not the stars, not the void, but the weight of forever motion. The struggle to remain human in a world that never stops moving and never truly arrives. No machine lasts forever. Bearings wear circuits, corrode radiation seeps through metal like invisible rust. On a generation ship, even the smallest failure could grow into disaster over centuries. A clogged valve, a corrupted program, a tiny leak in the air system, time would amplify them all. Entropy is the quiet enemy of motion. And in space there is no one left to call for help. To endure such a ship would need to recycle everything perfectly. But perfection is impossible. Microscopic loss accumulates, a fraction of oxygen here, a molecule of water there. The closed loop slowly opens and life begins to thin out. The passengers might not notice until it's too late, until the light in the hydroponic gardens dims, or the air tastes just a little too dry. In physics, entropy measures disorder. In human terms, it measures forgetting. Every rotation of the ship would grind its memory down a little more until even its purpose decayed into routine. In the end, the greatest challenge of a voyage through eternity isn't distance. It's keeping meaning alive while everything else falls apart. On Earth, balance is effortless. Forests breathe for animals, oceans cradle weather bacteria, renew the soil. Life persists because everything is connected, an unbroken loop that has refined itself for billions of years. But in space, that loop must be built by hand, and in every attempt the system eventually breaks. Biosphere experiments on Earth have already shown how fragile artificial balance can be. Oxygen levels drop, microbes overgrow, and plants suffocate in their own chemistry. Now stretch that fragility across centuries of travel. One species of algae too greedy, one bacteria too efficient, and the delicate equilibrium collapses. A world that's small can't correct its mistakes, it can only endure them until extinction. A generation ship would need to imitate Earth's biosphere perfectly, yet Earth itself barely holds together. The deeper truth is unsettling. Life doesn't exist despite chaos, it exists because of it. Strip away nature's unpredictability, and you lose the very resilience that makes life survive. In trying to control our own ecosystem, we may create one too perfect to live. When the journey outlasts a human lifetime, machines must become the true crew. They will steer, repair, and remember long after their creators are gone. At first they'll follow commands, program routines, protocols, and fail-safes. But centuries will stretch those instructions thin. Data will corrupt, sensors will decay, and sooner or later the machines will have to choose how to interpret the ghost of human intent. Perhaps they'll evolve, rewriting their own logic to preserve the mission even as the meaning fades. Perhaps they'll build new caretakers, descendants of metal still carrying the fragments of our purpose. The ship might arrive at another star one day, perfectly functioning, perfectly empty. The last human touch long erased, replaced by algorithms that no longer know who they serve. It's a haunting thought that our greatest voyage could succeed without us. The machines we made to carry our dreams might become the only witnesses of our passing caretakers of a memory they can no longer understand, yet still unable to stop moving toward a destination that no one remains to see. A generation ship would not fall apart in a single disaster. It would unravel slowly, not from broken machines, but from broken meaning. After centuries adrift, the original mission would fade into ritual. The stars outside would become myth. The destination a story told by elders to children who no longer believe. Without new horizons, faith turns inward, and the society that once reached outward begins to consume itself. Conflicts would grow where certainty once lived. Who decides what still matters when Earth is only a memory? Factions could form, those who want to continue, those who wish to turn back, and those who no longer care. On a world without seasons or sunsets, politics becomes theology. Every argument would echo through generations long after its reason was forgotten. Civilization depends on renewal, on discovery, on change, on a future that feels real. But on a ship lost between stars, there is only endurance. An endurance stretched too far becomes decay. The greatest danger of interstellar travel isn't failure. It's arriving nowhere together, believing we still remember why. When reason falters, belief takes its place. A ship drifting for centuries would need more than air and food to survive. It would need meaning. And in that endless dark meaning often takes the shape of faith. The voyage itself could become sacred, the ship a temple. The engine's hymns sung to whatever gods protect the metal from breaking. Over generations, the original purpose, exploration, discovery, hope might erode into scripture. The crew's descendants could worship the idea of motion, or the memory of Earth, or the distant star that never grows closer. Every control room might become an altar, every maintenance ritual a prayer. Myths would bloom like constellations within the ship's recycled air. Perhaps in the end that faith is not foolish. It would be the only thing powerful enough to hold a civilization together through centuries of silence. Science may have built the vessel, but belief, however fragile, would keep it alive. Because in the darkness between suns, even reason must kneel to the human need for hope. Purpose is fragile. It begins as fire, a shared vision that drives everything forward. But fire needs air, and on a journey without end, the air eventually runs out. Each generation born aboard the ship would live further from the memory of Earth, further from the dream that began the voyage. The mission would become a phrase recited without understanding, a tradition maintained out of habit rather than belief. Without purpose, order erodes. Work becomes routine, leadership becomes ritual, and curiosity fades into superstition. The descendants of explorers would turn inward, studying the ship's corridors as if they were the cosmos itself. Maybe they would stop looking at the stars, entirely finding comfort instead in the glow of their own machines. Civilization doesn't end with destruction, it ends with forgetting why it began. When motion replaces meaning, when a journey continues only because no one remembers how to stop, that is the true death of exploration. The stars no longer inspire. They only watch, silent witnesses to a purpose that burned out long before the light reached them. Time aboard a generation ship would stretch human life into something unfamiliar. Children would be born who never saw a planet, who learned to walk under artificial gravity and speak beneath ceilings of steel. To them, the ship would not be a vessel, it would be the universe itself. Stories of oceans, rain, and open sky would sound like myths from a forgotten paradise. Each generation would inherit not just the journey, but its consequences. Maintenance would become culture, preservation would become law. The young would grow old, performing the same duties as their ancestors, fixing the same machines, telling the same stories. Progress would vanish, replaced by survival. And yet perhaps in that sameness lies something enduring, a new form of humanity built not on change but on constancy. Still one question would linger across centuries. When the great-grandchildren of the first travellers finally see the light of another sun, will they recognise it as arrival? Or will they see it as betrayal, an interruption to the only home they've ever known? Centuries in isolation would reshape even the way people think. Language, that fragile vessel of memory, would splinter and evolve. The words spoken at launch would sound ancient foreign, perhaps even holy to their descendants. Manuals would turn into scripture, engineering logs would read like prophecy. Slowly the bridge between past and present would dissolve. Without fresh contact or cultural exchange, meaning itself would fragment. One generation might preserve the mission, the next might reinterpret it, the third might forget entirely. Even the name Alpha Centauri could fade, replaced by myths of a promised light, a star that waits for the worthy. The ship's control systems, written in a language no one alive can read, would become relics of gods who once knew how to move the world. And that is the cruelest truth of time. Knowledge does not survive distance. It must be renewed, taught, remembered. A ship can carry people through centuries, but without understanding it, only carries bodies, not civilization. In the silence of centuries, even the ship itself would transform from technology into legend. The engines that once roared with fire would become sacred artifacts. Maintenance drones might be worshipped as guardians. The ship's central AI, if it still functioned, could become the voice of prophecy its directives mistaken for divine will. The people aboard would no longer understand circuits or code, only that the heart of the ship must never be angered. Every command it issues would be obeyed without question. Over time, rituals would grow around its hum songs, prayers, offerings left at the glowing panels that once displayed navigation data. To the last descendants of Earth, the machine would no longer be a tool. It would be a god. The proof of its divinity would be simple and irrefutable. It keeps them alive. Perhaps in a way that belief would be true. For if the ship still moves, still sustains, then faith and function have become one. A fusion of mythology and engineering, keeping humanity alive long after memory itself has died. When knowledge fades, power fills the void. A generation ship without history would need new rulers, not engineers or scientists, but interpreters of mystery. Those who claim to understand the machine's will would rise above the rest, forming a priesthood around survival. Maintenance becomes ritual, obedience becomes sacred, and hierarchy replaces curiosity. Old technologies would be used without comprehension, passed down like sacred relics. A button pressed, a lever pulled actions preserved not because they're understood, but because they work. And when they stop working, fear replaces logic. Sacrifice becomes policy, and rebellion becomes heresy. Civilization in its most fragile form would regress not through violence, but through faith in procedure. Humanity's greatest creation, a ship meant to explore the stars, could end as a drifting cathedral ruled by myths born from ignorance. The same engines that once carried reason across the cosmos would now echo with prayers for light that no one remembers how to ignite. After enough centuries, the ship would grow quiet, not from malfunction, but from exhaustion. The rituals would continue, but the meaning behind them would fade completely. The engines would pulse faintly, more out of habit than purpose, tended by descendants who no longer question why. Generations would live and die within corridors whose builders had long since become legends. Inside language would narrow to the practical. Words for food, for air, for light. Concepts like planet or sky would vanish, replaced by terms for the only world they know, the ship, the core, the great metal. They would look upon stars with indifference, like ornaments on a ceiling that has always been there. And in that stillness, humanity's brightest dream would become a quiet loop of existence. No conflict, no discovery, no memory of motion. The stars would continue to burn outside patient and unbothered, while inside the vessel the last echo of our species would live out its final centuries in peaceful, perfect ignorance. One day, maybe after 1,000 years, the ship would finally reach its destination. Alpha Centauri's light would fall upon its hull, soft and golden after an eternity of darkness. But no one aboard would notice. The stars outside would mean nothing to them now. They are part of the background, eternal and irrelevant. The vessel would continue to drift, following ancient routines written by hands long turned to dust. The navigation systems might still hum quietly, awaiting commands that will never come. Doors will still seal. Gardens will still glow under artificial suns. Everything will work, but nothing will understand why. Outside, the new world would wait oceans untouched, continents unclaimed. Within reach of paradise, the descendants of explorers would remain asleep in their ignorance, orbiting forever, too complete in their isolation to ever set foot on the world their ancestors once died dreaming of. Yet perhaps one day something shifts. A child curious beyond measure looks at the stars and wonders what they are. She asks questions no one can answer: why the light moves, why the engines hum, why their world has no sky. Curiosity buried for centuries stirs again like a spark under ash. She finds forbidden places, old corridors sealed for generations, chambers of rust and silence. There she discovers relics, words etched into metal, faded images of oceans, forests. Faces that look like hers but stand beneath open air. The records mean nothing to her language, but something in her heart understands. These were people who left somewhere. These were people who chose to travel. And in that single moment of recognition, the dream wakes again. Not fully, not clearly, but enough. A thought that once built worlds flickers alive in one fragile mind. We came from somewhere else, and from that thought, the long night begins to end. The child grows and her questions spread like a quiet contagion. Others begin to wonder, to dig, to listen to the whispers of machines that once spoke clearly. Old panels flicker with meaning. Fragments of language are pieced together. Diagrams once mistaken for scripture are recognized as blueprints. What was holy becomes human again. They learn that their metal world was built, not born. That the stars outside are not decorations but suns. And that one of them, brighter and closer, is where their ancestors meant to go. The revelation is terrifying. Every certainty collapses. The myths crumble, and in their ruins something new takes root. Purpose. Soon they will face the same questions their ancestors asked: how to survive, how to move, how to begin again. But this time the goal will not be escape. It will be return not to Earth itself, but to the idea of discovery. To remember that motion was never meant to trap them. It was meant to lead them home. With purpose reborn, the old vessel stirs to life. Generations raised in silence begin to map the heavens again, naming constellations their ancestors once knew. They learn to read the ship's instruments, relics of an age when humanity still spoke with the language of science. Numbers and orbits replace prophecy. Light becomes knowledge once more. They find the records of the destination, Alpha Centauri, a system with 3 suns, one warm enough to hold life. For the first time in 1,000 years, they understand where they are and how close they've always been. Yet the revelation carries both hope and sorrow. The journey that once defined them was already complete long before they were born. As they gather around the observation decks, watching the triple star burn like a crown in the distance, something ancient stirs in their hearts, the same awe that once pushed their ancestors into the unknown. And for the first time in ages, someone dares to say the words aloud. Let's go there. Engines that slept for centuries awaken with trembling light. Systems long forgotten shudder, realign and hum as if remembering their purpose. The sound echoes through the corridors, a pulse, a heartbeat, something alive once more. For the first time in living memory, the ship moves. The people watch through windows their ancestors once built, seeing the stars shift tiny but real. Children press their hands to the glass, feeling the vibration of power beneath their palms. What was once sacred fear becomes awe again. The machine is no longer a god, it is a companion, a thing they understand and now command. Every deck fills with stories, voices, anticipation. They do not know what awaits beyond, only that they must go. For the first time in 1,000 years, humanity's oldest instinct returns, not survival, not faith, but curiosity. The great ship turns steady and slow toward the golden light that was always waiting for them. As the ship drifts closer, the faint golden light grows into a sunrise no one aboard has ever seen. Alpha Centauri fills the viewports, vast, radiant, alive. Its light seeps through the corridors like something holy, touching faces that have only ever known artificial glow. The people fall silent, overwhelmed, not by fear but by recognition. For the first time they understand what the word star truly means. The sensors confirm what the myths once promised. A world below blue and green orbiting one of the suns. A world where air moves, where gravity feels like embrace, where dawn and dusk follow each other in endless rhythm. The ship's engines slow, and for a moment it seems as though time itself pauses, a breath held across 1,000 generations. Then gently humanity returns to the light. The vessel that left Earth so long ago, a tomb, a temple, a memory, finally becomes what it was always meant to be, a bridge between what we were and what we will become again. They descend through clouds that have never known human touch. The ship's hull glows against the atmosphere, a streak of light falling through centuries. Below, oceans shimmer, forests breathe, and mountains wait silent witnesses to a home no one remembers, yet somehow feels familiar. When the first explorers step onto the new world, the air shocks them, rich, living, full of scent and sound. The soil is warm beneath their hands. For a moment they simply stand there, unable to speak, watching the sunrise that their ancestors dreamed of but never saw. In the light, humanity is reborn. The stories of Earth return not as history but as instinct. The idea that once carried them across the void, curiosity blooms again, stronger than ever. 1,000 years of darkness dissolve in a single dawn, and as the sun climbs higher, one truth becomes clear. The universe was never waiting for us to arrive. It was waiting for us to remember how, for the first time in 1,000 years, humanity breathes under an open sky. The air tastes wild, full of scent, moisture, and sound. Wind moves freely again, brushing against skin that has only known recycled air. Above them, clouds drift in shapes no one remembers, and the sun burns without glass between. It is not Earth, but it feels like forgiveness. The settlers wander in silence at first. Some touch the soil with trembling hands. Others stand and cry without knowing why. Their ancestors dreamed of this, a sky, a horizon, a beginning. Yet the moment feels heavier than triumph, because what they see is not conquest but return, a reminder that the stars were never meant to be destinations, only mirrors showing what it means to begin again. As the night falls and the first constellations rise, they name them not after gods or heroes but after the things they lost: memory, faith and home. And in that quiet act, humanity learns once more that discovery has never been about where we go but who we become along the way. Days turn into weeks and the settlers begin to build simple shelters, at first shaped from the wreckage of their ship, then gardens, then fire. The land accepts them, cautious, patient, as if waiting to see what kind of creatures have returned to the light. Rivers shimmer under twin suns, carrying minerals older than their species. Strange plants bloom in alien colours, bending to a wind that hums in a different key. They name the world Aurora after the first light they saw upon landing. Every morning the horizon glows with that name, and every evening the stars remind them what it cost to reach this peace. They keep their technology, but use it sparingly, like a language they no longer need to speak every day. The old ship stands on a hill above their new home, its hull burned and silent, a monument to the distance between ignorance and understanding. And beneath that sky, humanity begins again, slower, quieter, wiser. For the first time, we're not visitors among the stars. We are part of them. Before the ship's systems finally go dark, the settlers gather everything. It remembers the languages, the faces, the failures and triumphs of 1,000 years. They call it the Archive of Light. Within its data cores are the last images of Earth, the first diagrams of the voyage, and the final recordings of those who never saw the new sun. They know this knowledge cannot survive forever. Metal corrodes, memory fades, and someday even Aurora's mountains will fold back into dust. But they pass the archive down anyway, copied, rewritten, retold, because the story matters more than the data. What endures isn't precision, but the act of remembering. Each generation will lose a little more, just as the first did, but they will also gain something the ancestors never had: peace. The archive is not a warning nor a prophecy. It is a mirror, a reminder that humanity once reached for the impossible and in doing so became something new. One night beneath the twin suns, they build a transmitter on the hill beside the old ship. Its power is small, its reach uncertain, but that doesn't matter. They point it toward the dark between the stars, toward the pale blue memory of where it all began, and they speak. The message is simple, carried in every language they still remember. We made it! No coordinates, no request for reply, only a whisper of completion across the endless night. The signal will take more than 4 years to reach Earth if Earth still listens. But maybe that's not the point. The message isn't for those who stayed behind, it's for the universe itself. They send it not as a cry of triumph, but as gratitude. For the stars that guided them, for the silence that tested them, and for the light that finally received them. And as the transmitter's beam fades into the void, humanity leaves one last echo in the cosmos, a promise that the journey was never in vain. Centuries later, Aurora will have cities, oceans crossed by sails, skies filled with quiet lights. Children will grow up knowing both the warmth of the sun and the memory of the stars. They will tell stories of a people who came from the dark, who carried fire through the cold to find a second dawn. The ship will still stand on its hill, half buried and gleaming beneath starlight, a relic of both fear and faith. By then, the distance to Earth will be meaningless. The journey that once seemed impossible will have become history, then legend, then myth. What mattered was never the crossing itself, but what humanity discovered in the crossing, that meaning isn't found in reaching a place but in refusing to stop searching. And as night falls over this new world, a child will look up at the sky and ask where home is. An elder will smile and point upward, saying softly, everywhere we remember the light. For as long as humans have looked up at the night sky, one question has burned brighter than the stars themselves. Are we alone? In ancient times it was a matter for myth and philosophy. Some imagined gods walking among the constellations, others believed Earth was the only world unique and isolated. But as centuries passed and science replaced myth with measurement, the question did not fade. It grew sharper and more urgent because the universe kept growing around us. 400 years ago, Galileo lifted a telescope and found moons orbiting Jupiter. Suddenly Earth was not the center. 2 centuries later, astronomers saw faint stars wobble and realized they might host planets. By the 20th century, spacecraft had flown past every world in our solar system, and yet not one showed unambiguous signs of life. Mars was dry, Venus was a furnace. The outer moons, though intriguing, remained beyond reach. The silence deepened the mystery. Then came the revolution. In the 1990s, using delicate measurements of starlight, astronomers confirmed the first planets orbiting other suns. They were nothing like Earth gas giants orbiting scorchingly close to their stars, hot Jupiters defying all expectations. But the discovery changed everything. If planets existed elsewhere, then Earth could not be the only one. The universe might be crowded with worlds. The count grew quickly. With improved instruments, thousands of exoplanets were discovered, ranging from small rocky worlds to giant planets bigger than Jupiter. Some orbited stars like our own sun, others circled dim red dwarfs. A few lay in the so-called habitable zone where temperatures could allow liquid water. For the first time, the idea of life beyond Earth shifted from speculation to calculation. We now had statistics, probabilities, catalogues of worlds that might be living or lifeless. And yet numbers alone are not enough. To know whether a planet can host life, we must look at its atmosphere. Gases can betray the presence of biology. Oxygen, methane, water vapor when found together in disequilibrium, they whisper of processes beyond geology. The problem was that earlier telescopes were not powerful enough. Hubble could glimpse atmospheres in broad strokes, but it could not disentangle the details. We needed a new eye sharper and steadier, tuned to the wavelengths where these molecules leave their fingerprints. That eye is James Webb. With its golden mirrors and infrared vision, Webb can capture the faint light of a planet passing in front of its star. And from that light read the chemistry of alien skies. For the first time in history, we have an instrument capable of searching for the signatures of life not in our solar system, but across the galaxy. This is the turning point. The question that haunted philosophers, inspired poets, and drove explorers has become an experiment. We can measure it. We can test it. We can begin to answer not with stories but with spectra. And so the search begins. From the glowing giants of distant systems to the quiet, temperate worlds that might resemble our own web, has opened a doorway into the most profound investigation humanity has ever attempted: the hunt for alien life. When the first exoplanets were confirmed, many expected that signs of intelligent life would follow quickly. The logic seemed simple. If there are countless stars and many of them have planets, surely some of those planets must host civilizations. And if civilizations exist, would they not send signals, perhaps radio broadcasts echoing across the galaxy? This idea gave rise to one of the boldest scientific efforts of the 20th century: SETI, the search for extraterrestrial intelligence. The method was straightforward in concept. Astronomers would point radio telescopes at the sky and listen. If an advanced civilization was transmitting intentionally or accidentally, we might pick up a faint whisper. After all, Earth itself leaks radio noise into space. Television signals, radar beams, communication chatter. If we do it, why not them? The earliest searches in the 1960s targeted nearby stars. They were limited, listening only to narrow ranges of frequency. The results were silent. Decades passed and the silence deepened. Larger projects followed. The giant Arecibo dish in Puerto Rico, the Allen Telescope Array in California. International collaborations scanning millions of frequencies simultaneously. Yet the outcome was always the same. No confirmed signals, only occasional bursts of noise later traced to natural phenomena or earthly interference. The silence was unsettling. It was summarized in the famous Fermi paradox. If the galaxy is filled with life, where is everyone? With hundreds of billions of stars, even a tiny fraction producing civilization should have filled space with chatter. Instead, our telescopes heard only the hiss of cosmic background radiation. Some scientists argued this silence was meaningful. Perhaps intelligent life is rare, fleeting, or chooses not to broadcast. Others suggested we may not be listening correctly. What if alien civilizations communicate with technologies we cannot yet imagine? What if their signals are encrypted, hidden, or so different from our own that we mistake them for noise? The possibilities are endless, but the evidence remains absent. Despite the silence, SETI taught us something vital. The search for life cannot rely solely on waiting for others to call. We must learn to recognize life indirectly through its impact on planets and atmospheres. The chemistry of a sky does not need to intend communication, it simply exists. Oxygen from forests, methane from microbes, carbon dioxide cycles, water vapor from oceans. These are signatures that any telescope tuned properly can read. This realization shifted the focus from intelligence signals to biosignatures. Instead of hoping for alien broadcasts, we now look for alien biology. And here James Webb enters the stage. Where radio telescopes listen for deliberate voices, Webb observes the unintentional breath of life itself. It does not wait for a message. It reads the sky. The lessons of SETI still matter. They remind us that the universe may not be eager to reveal itself, that discovery may require patience and persistence, but they also remind us that silence is not emptiness. Silence may simply mean we have not yet learned the right way to listen. Webb gives us that new way, and so the story moves forward from radio whispers to infrared spectra, from listening to light. The question remains the same, but the methods have evolved. Humanity is no longer just an eavesdropper on the cosmos. With Webb, we are investigators examining worlds themselves for the traces of breath chemistry and life. The discovery of exoplanets was not just a milestone. It was an earthquake in astronomy. For centuries, the existence of other worlds was a matter of speculation. Then suddenly, in the last few decades, planets began to appear everywhere. The revelation was as if the universe had been hiding a vast population waiting for us to build instruments sensitive enough to notice. The first confirmed detections in the 1990s stunned astronomers. One planet circled a pulsar, the dense spinning corpse of a dead star. It was a bizarre place for a planet to exist, and yet there it was. Soon after the first hot Jupiter was found, a gas giant orbiting so close to its star that a year lasted only a few days. No one had predicted such a world. The discovery shattered theories of planetary formation. As more planets were detected, the diversity became overwhelming. There were super-Earths larger than our planet but smaller than Neptune. There were mini-Neptunes, icy worlds with thick envelopes of gas. There were lava worlds with molten surfaces glowing under the heat of nearby suns. Some planets orbited double stars like Tatooine from science fiction. Others traced eccentric paths swinging wildly closer and farther from their stars. The universe, it turned out, was more imaginative than our textbooks. The Kepler Space Telescope transformed the field. By staring at a patch of sky for years, it recorded tiny dips in starlight as planets crossed in front of their stars. Kepler revealed thousands of worlds showing that planets are not rare, they are the rule. Practically every star hosts at least one. Many stars have entire systems, some with architectures stranger than anything in our own neighbourhood. From this flood of data, astronomers began to classify. Planets were grouped by size, orbit, and composition. Rocky Earth-sized planets, gas giants, sub-Neptunes, worlds in the habitable zone where conditions might allow liquid water. But classification was only the first step. To understand whether these worlds could host life, we needed to move beyond counting and start characterizing. What were their atmospheres made of? Did they have oceans, clouds, or storms? Did they carry the chemical imbalances that suggest biology? That is where James Webb enters the story. While Kepler and its successors revealed the sheer abundance of planets, Webb provides the detail. It can take those silhouettes against starlight and transform them into spectra lines and patterns that reveal chemistry. Instead of just knowing a planet exists, we can begin to know what it is like. This shift changes everything. No longer are exoplanets dots on a chart. They become places, worlds with weather history and potential. Some are scorching, some frozen, some tempestuous, some calm. Each one is a laboratory in the grand experiment of nature. Each one is a chance to ask, could life take root here? And among this multitude of worlds, Webb has already found targets that capture the imagination. A hot Jupiter with sulfur dioxide clouds. A sub-Neptune with methane and carbon dioxide. A world where hints of exotic molecules appear faint and fragile, yet suggestive of something more. These first results are only the beginning. The catalogue is vast and Webb has years ahead to explore it. The search for life is no longer about Earth alone. It is about context, about seeing our planet as one data point among thousands. And as the list grows, the odds shift. Life may not be rare. It may be common, written into the physics of chemistry and starlight. We do not know yet, but for the first time we have the means to find out. To search for life, we must learn to read the skies of distant worlds. This is where James Webb excels, using a technique both elegant and powerful: transmission spectroscopy. The method begins when a planet passes directly in front of its star. As it transits, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. That light carries information etched with the fingerprints of molecules. Every gas absorbs specific wavelengths. Water vapor leaves dips in one part of the spectrum, methane in another, carbon dioxide in yet another. By spreading the light into a rainbow and analysing the faint variations, astronomers can deduce the chemical composition of alien skies. It is as though the planet is whispering its secrets and Webb is trained to listen. The challenge lies in precision. The effect of an atmosphere on starlight is minuscule, often less than a fraction of a percent. Earlier telescopes like Hubble and Spitzer could attempt these measurements, but their data were noisy, their resolution limited. Webb's infrared instruments, stable and exquisitely sensitive, change the game. They can detect the smallest wiggles in a spectrum, turning uncertainty into clarity. One of Webb's first triumphs came with the hot gas giant WASP-39b. observations revealed a rich spectrum, not only water vapour but also carbon dioxide and sulfur dioxide. The latter was especially striking as it was the first clear detection of photochemistry on an exoplanet. Starlight interacting with the atmosphere had produced new molecules reshaping the chemical landscape. It was proof that Webb could not only detect gases but also witness chemistry in action. Another landmark was K2-18b, a sub-Neptune orbiting in the habitable zone of a red dwarf star. Webb's data showed methane and carbon dioxide with tentative signs of dimethyl sulfide, a compound on Earth produced primarily by marine plankton. The detection is debated, uncertain but electrifying. Even the hint that Webb could glimpse such a molecule across light years shows the leap we have made. These results confirm the power of the method. For the first time, we're not only detecting exoplanets but describing them in detail. We know their skies contain water, carbon, sulfur, and perhaps more exotic chemistry. Each new spectrum is a step toward identifying worlds that may carry the breath of life. And this is only the beginning. Webb will apply transmission spectroscopy to dozens of planets, hot Jupiters, warm Neptunes, rocky super-Earths. Some will reveal thick atmospheres shrouded in clouds. Others may show bare rocks stripped of gases by stellar winds. Each outcome teaches us something about habitability, about what makes a planet stable, fragile, or alive. To imagine what comes next is staggering. One day, perhaps not far, spectrum may arrive that shows oxygen alongside methane or water, alongside ozone, a chemical imbalance hard to explain without biology. That would be the moment the search for life moves from possibility to detection. Webb has not reached that milestone yet, but it has opened the path. From a faint dip in starlight across unimaginable distances, we're learning to read the invisible. It is science at its most delicate and its most profound. To claim we have found life is no small thing. The universe is filled with processes that can mimic biology, and every molecule we search for has both living and non-living origins. That is why astronomers tread carefully. They speak not of proof, but of biosignatures, chemical clues that taken together may point toward biology. The classic example is oxygen. On Earth, oxygen is abundant only because plants and microbes constantly produce it. Left alone, it would quickly bind with rocks or escape into space. Finding oxygen in an alien atmosphere would be exciting. But oxygen can also arise from non-biological processes such as ultraviolet light breaking apart water molecules. By itself, it is suggestive but not decisive. Methane tells a similar story. On Earth, much of it comes from microbes, but volcanoes and chemical reactions deep underground can produce it too. The real power lies not in individual gases, but in combinations. When oxygen and methane coexist in large amounts, they are unstable together. One should destroy the other. Their simultaneous presence implies something is replenishing them, a disequilibrium that on Earth biology maintains. Water vapor, carbon dioxide, nitrous oxide, ozone. Each has its own story, its own pitfalls. What scientists seek are patterns, ensembles of gases that defy easy geological explanations. It is less about spotting a single molecule, and more about reading the balance of a planet's atmosphere the way a doctor reads vital signs. The patient may not speak, but the body reveals the truth. This is why Webb's results are so important. For the first time, we can measure these gases with the precision required to test for disequilibrium. We can ask whether a planet's chemistry is stable or out of balance. We can begin to separate the possible from the probable. Already in the tentative hints from K2-18b, we see the potential of this approach. Even a disputed detection of dimethyl sulfide is enough to change the conversation. It shows that biosignature science is no longer theoretical. It is operational. Yet caution remains. Astronomers know the dangers of false positives. A planet with unusual geology or bathed in the radiation of an active star could mimic life's chemistry. That is why multiple observations, repeated transits, and cross-checks with other instruments are essential. One spectrum can be a tease. Many spectra, consistent and clear, can build a case. The quest for biosignatures is a slow, careful process more like a trial than a revelation, but it is also thrilling. For the first time, humanity is gathering the evidence required to argue the case for life beyond Earth. Each observation is a piece of testimony, each gas a witness. And beyond the science lies the anticipation. Imagine the moment when a spectrum arrives and the pattern is undeniable. Oxygen, methane, water in disequilibrium across light years of space. No announcement in history could carry greater weight. Webb has not given us that moment yet, but it has brought us to the threshold where the possibility is real. The question is no longer whether we can search for life. It is how we will interpret the answers when they come. When we imagine life beyond Earth, it is tempting to picture another blue planet with oceans, forests, and skies like our own. But the universe may not be so narrow in its creativity. Life could arise in forms unfamiliar, built on chemistries and conditions we have barely considered. To search only for copies of Earth would be to limit our imagination. On Earth, life is based on carbon. Carbon's ability to form complex, stable molecules makes it ideal for biology. But could silicon play a similar role elsewhere? Silicon abundant in rocks and sand also bonds with multiple elements. In theory, silicon-based life could exist, though its molecules tend to be less flexible than carbon's. Perhaps in environments hot enough to keep silicon compounds fluid, some form of alien metabolism could emerge. Water, too, is central to our definition of life. It dissolves chemicals, carries nutrients, and stabilizes temperatures. But water is not the only solvent in the cosmos. Ammonia, methane, or even sulfuric acid could play similar roles under the right conditions. Saturn's moon Titan, with its methane lakes and nitrogen atmosphere, offers a glimpse of this possibility. If biology can arise in such exotic chemistry, Webb's instruments might detect unusual gases or spectral features that betray its presence. Even within carbon, water life diversity is immense. Microbes thrive in boiling springs, in the crushing darkness of the deep ocean, in acidic pools, and even inside rocks. Life on Earth has colonized extremes once thought impossible. If Earth can harbor such resilience, what might alien worlds achieve? A planet scorched by radiation might evolve organisms with protective pigments. A frozen moon might shelter subsurface oceans warmed by tides. Biology is resourceful and evolution relentless. For Webb, this means keeping an open mind. The telescope does not know what life is. It only measures light, but in that light may be hints of chemistries we do not yet understand. An atmosphere rich in unexpected compounds, or a spectrum that refuses to match our models, could signal not an error, but a new kind of biology. Recognizing it will demand both caution and creativity. This is why scientists often speak of agnostic biosignatures, signals that indicate complex processes, even if we cannot immediately identify them as familiar life. Patterns that defy simple physics or geology may be the fingerprints of something new. Webb may not deliver proof, but it can deliver anomalies, and anomalies are where discovery begins. The great lesson of astrobiology is humility. Life may be stranger than our stories, stranger even than our science. This search is not about confirming Earth's uniqueness, but about testing whether nature has written many versions of biology across the cosmos. And in this search, Webb is our first great tool. It gives us the ability to ask with data rather than dreams. Is there only one way to be alive, or are there countless? The search for life is not only about single discoveries, it is about building a framework, a map of possibilities that tells us where to look and what to expect. Before Webb, exoplanets were mostly catalogued as points of data, a size and orbit, perhaps a rough mass. Now with Webb's precision, we can begin to sort them into categories defined not only by physics but by chemistry and climate. Hot Jupiters were the first exoplanets to dominate discoverers, massive gas giants orbiting perilously close to their stars. They are blasted by radiation, their atmospheres swollen and turbulent. Webb has revealed the fine details of these giants. Winds roaring at thousands of kilometers per hour, chemical cocktails of carbon dioxide, sodium sulfur dioxide, and even glassy silicates. They are hostile, uninhabitable, yet essential. They test our models of atmospheric dynamics under extreme conditions. Further out are warm Neptunes and sub-Neptunes, smaller gas or ice giants, that often defy comparison to anything in our solar system. Many of them have thick atmospheres, but Webb's spectra are beginning to distinguish which are hazy, which are clear, and which might contain traces of water vapor or methane. These worlds may not host life as we know it, but they are laboratories for understanding how planets retain or lose their gases. Then come the rocky super-Earth's planets, larger than Earth, but smaller than Neptune. These are among the most tantalizing because their size suggests solid surfaces and potential atmospheres. Webb's instruments are already probing some of these worlds, though clouds and hazes often veil their spectra. Even so, the effort marks a step closer to the Holy Grail, an atmosphere rich in water, oxygen, or methane around a rocky planet in the habitable zone. Among red dwarf stars, the most common in the galaxy, Webb is targeting small planets where conditions might allow liquid water. These stars are dim, making their planets easier to study in transit. They are also volatile blasting flares that may strip atmospheres or sterilize surfaces. Webb's data will help us learn which red dwarf planets are resilient and which are doomed, a key question since billions of them dot the Milky Way. Together, these studies are not random. They are building a comparative atlas of planets. Just as biologists classify species to understand evolution, astronomers classify planets to understand habitability. Which combinations of mass orbit and atmosphere create stable climates? Which lead to runaway greenhouses or frozen wastelands? Where does Earth fall in this spectrum and how rare or common is it? This is the heart of Webb's role. It transforms the exoplanet field from a list of curiosities into a science of patterns. Once patterns are clear, predictions follow. We will not only know what kinds of planets exist, but also where to focus the search for life. And as those patterns emerge, a new question arises. If planets like Earth exist, how do we recognize the truly special ones? The worlds that not only could host life, but perhaps already do. The phrase habitable zone has become almost mythical. It is the ring around a star where a planet could in theory sustain liquid water on its surface. Too close and water boils into steam. Too far and it freezes into ice. Within this Goldilocks zone, conditions may be just right. It is the simplest and most powerful filter astronomers use when scanning thousands of worlds. Water is central because on Earth it is the universal solvent of life. It carries nutrients, supports chemistry, and shapes climates. Without liquid water, life as we know it struggles to take hold. That is why the habitable zone is often called the life zone. Webb targets many of these planets, hoping to read their atmospheres for signs of water vapor, oxygen, or methane. But habitability is not as simple as distance. A planet in the right zone may still be barren. Venus orbits within the Sun's habitable zone, yet its atmosphere has turned it into a hellscape of sulfuric acid clouds and crushing heat. Mars, just on the outer edge, once had rivers and lakes, but its thin atmosphere let its oceans escape. Position matters, but so do mass geology, magnetic fields, and atmospheric stability. Webb's role is to refine the concept. By studying planets across different zones and comparing their atmospheres, it teaches us that habitability is a spectrum, not a switch. Some planets may hover on the edge, teetering between stability and collapse. Others may cycle between wet and dry eras. Webb's instruments can detect these subtle differences, showing that being in the habitable zone is a beginning, not a guarantee. What this means is profound. Earth-like conditions may be rare even among Earth-like orbits. The life zone is a necessary filter but not the final word. We must look deeper past the orbit into the sky itself. The paradox becomes clear when we compare planets. Some lie squarely in the habitable zone yet are hostile. Venus should be temperate, but its greenhouse effect is catastrophic. Mars should be marginally habitable, but its lack of atmosphere left it dry and cold. Meanwhile, moons like Europa and Enceladus orbit far outside the Sun's habitable zone, yet they may harbour oceans beneath icy shells warmed by tidal flexing. The rulebook is more complicated than we thought. This is why Webb's mission is not only to confirm theories, but to challenge them. Its infrared eyes can probe for water vapor even in unexpected places. It can detect carbon dioxide in thin atmospheres or identify hazes that trap heat. By expanding our survey beyond the textbook life zones, Webb reminds us that habitability is creative. Life may find ways to exist in niches far stranger than Earth. Consider red dwarf stars. Their habitable zones are tight and close. Planets there risk tidal locking, with one side scorched and the other frozen. Yet if an atmosphere circulates heat efficiently, such a world could still support oceans. Webb will test these possibilities, searching for balance where physics suggest extremes, or consider rogue planets wandering through space without stars. By traditional definitions, they should be sterile. But if they carry thick atmospheres or internal heat, could they hide warm environments beneath? Webb may never detect life on such worlds directly, but its discoveries force us to expand our imagination. The lesson is clear. The habitable zone is a guidepost, not a verdict. Life may thrive outside its borders and planets within it may perish. What matters most is not distance, but the delicate balance of atmosphere, chemistry, and energy. Webb is teaching us to stop looking only for Earth's twin, and to start looking for Earth's cousins, diverse, imperfect, but still alive. The search for biosignatures is as thrilling as it is treacherous. Each molecule detected in an alien atmosphere carries the promise of discovery, but also the danger of misinterpretation. The universe is clever at disguising geology as biology, and the line between the two is razor thin. Take oxygen, for example. On Earth, its abundance is sustained by photosynthesis. Without life, it would vanish from our air in a geological blink. So astronomers long assumed oxygen would be the smoking gun of alien biology. But Webb's work, combined with theoretical models, reminds us of caution. Ultraviolet radiation can split water molecules, allowing hydrogen to escape into space while oxygen accumulates. A dead, desiccated world could masquerade as alive. Methane offers another puzzle. On Earth, microbes are prolific methane producers, but volcanoes' hydrothermal vents and chemical reactions in a planet's mantle can also release it. Finding methane alone is not enough. Even methane with carbon dioxide is not decisive because geologic activity can mimic that pairing under certain conditions. Only when multiple gases coexist in unstable equilibrium do the odds tilt toward biology. The case of K2-18b shows this dilemma perfectly. Webb's data hinted at methane carbon dioxide and even traces of dimethyl sulfide, a compound that on Earth is tied almost entirely to life. The announcement sparked excitement but also skepticism. The signal was faint on the edge of detection. Noise clouds or unexpected atmospheric chemistry could explain it. Scientists stress that more observations are needed and the debate continues. This is science at its core, cautious, incremental, but daring. A single spectrum can inspire headlines, but Webb's role is to build evidence to repeat observations until patterns emerge. Biosignatures are not about one molecule in isolation. They are about ensembles, balances, disequilibria that defy geology, and even then, interpretation requires humility. False positives are only half the problem. There is also the risk of false negatives. Life may exist, but in forms we do not recognize. Its chemistry may not announce itself in oxygen or methane. It may use molecules we consider inert or operate in solvents other than water. To dismiss a world as sterile simply because it lacks our familiar gases could be just as misleading as declaring life too soon. Webb's task, then, is not to deliver a final verdict, but to map the possibilities, to show us which planets deserve more attention, which atmospheres whisper of imbalance, which signals demand deeper scrutiny. It provides the clues, but the interpretation will be a generational effort weaving together astrophysics, chemistry, and biology. The thrill lies in the uncertainty. Each new detection is both a promise and a puzzle. Are we glimpsing biology across light years, or merely the tricks of geology under alien suns? The answer will not come easily, but for the first time we have the tools to ask the question seriously. and that alone is revolutionary. Not every spectrum Webb collects fits neatly into our expectations. Alongside the triumphs of clear detections come puzzles, strange patterns, unusual signals, data that resist easy interpretation. These anomalies remind us that discovery is not only about confirming what we predict, but also about confronting the unexpected. Some of these mysteries come from the atmospheres of exoplanets. Webb has detected hazes that are thicker than models, predict masking signatures of gases we expected to see. On certain hot Jupiters, the clouds appear to be laced with exotic particles, silicates metals creating spectra that look nothing like Earth's skies. On others, the atmospheres seem strangely muted, their features flat and ambiguous, as if something is erasing the chemical fingerprints before they reach us. Are these planets shrouded in global smog, or do they represent a chemistry we have yet to model correctly? Even more intriguing are the faint fleeting features. In some cases, Webb has caught glimpses of absorption lines that hint at unusual molecules, compounds that on Earth would be unstable or rare. These detections are tentative, hovering at the edge of certainty, but they tease the imagination. Could they represent exotic photochemistry under alien suns? Or are they simply noise masquerading as signal? The line is thin and only repeated observations can decide. Occasionally, Webb's data have revealed atmospheric dynamics that defy expectations. Some planets show winds so powerful that heat is redistributed in patterns our models cannot yet explain. Others show temperature inversions where upper layers are hotter than lower ones, contrary to what theory predicts. These quirks remind us that every atmosphere is a laboratory, and many do not obey Earth's rules. Beyond exoplanets, Webb's deep field surveys have also turned up the unexpected. Galaxies appearing older, brighter, or more massive than models allow. Star formation rates that seem impossibly high. Quiescent galaxies that look dormant when they should still be alive with activity. Each one is a challenge to cosmology, but also a clue. Perhaps our models are incomplete. Perhaps the universe has tricks we do not yet understand. And then there are the transients. Brief flashes of light, unexpected brightenings or sudden dimmings. Some may be supernovae or active black holes. Others remain unexplained. Webb is sensitive enough to capture signals that no other telescope can confirm, leaving astronomers with tantalizing data points that resist classification. What unites these anomalies is possibility. In the past, strange results were often dismissed as errors. Now with Webb's precision, they demand attention. Each unexplained feature may be the seed of a new discovery, an invitation to rethink assumptions. They remind us that the universe is not obligated to match our expectations. It writes its own story, and sometimes that story surprises us. These puzzles are not failures. They are the frontier. Every mystery Webb reveals expands the space of questions we can ask. And in those questions lies the future of discovery. The true power of Webb lies not only in single discoveries but in comparisons. A lone spectrum can be intriguing, even breathtaking, but its meaning grows richer when placed beside dozens of others. Patterns begin to emerge and patterns tell stories. Through comparison, Webb is transforming the study of exoplanets from a collection of curiosities into a coherent science. Already astronomers are assembling catalogues of spectra from hot Jupiters, warm Neptunes, and rocky super-Earths. When viewed together, the similarities and differences stand out. Some hot Jupiters show clear signatures of water and carbon dioxide, while others are muted by hazes. Some sub-Neptunes appear cloaked in thick atmospheres, while others seem stripped bare. Even among planets of similar size and orbit, the diversity is staggering. This diversity is not random. It encodes the history of each world. A planet rich in carbon dioxide may have undergone volcanic outgassing. One with sulfur dioxide could be shaped by intense stellar radiation. A planet with water vapor might hint at oceans below. By comparing many planets, Webb allows scientists to test which factors matter most. The type of star, the planet's mass, the distance from its sun, or the violence of its past. This comparative approach is essential to the search for life. We cannot know in advance which conditions are truly hospitable, but by mapping the full range of planetary atmospheres, we begin to see the boundaries of possibility. If water vapor is common, then potential habitability may be widespread. If methane is rare, perhaps biology is too. Each new world adds a point to the graph, tightening the constraints on what life requires. It also reframes Earth. In isolation, our planet is special, filled with oceans, oxygen, and life. But in context, Earth becomes one data point among thousands. By studying exoplanets, we learn not only about them, but about ourselves. Why does Earth have stable oceans while Venus boiled and Mars froze? Why did biology flourish here and nowhere else we know? Webb's comparative surveys are a way of answering these questions through cosmic statistics. The telescope's legacy will not be a single planet declared alive or dead. It will be a planetary atlas, a grand map of atmospheric chemistry across the galaxy. From this map, future telescopes can target the most promising candidates, narrowing the search for true biosignatures. Webb is the scout laying the foundation for explorers yet to come, and in this growing atlas there may already be hints of where to look next. Planets that stand out from the crowd, worlds whose chemistry whispers of imbalance, candidates that demand follow-up. The future of the hunt for life will not be about chance, but about strategy guided by the patterns Webb is revealing now. James Webb has opened the door, but it will not walk the path alone. The search for life is a relay, and other instruments are already preparing to take the baton. Together they will turn Webb's hints into certainty, its puzzles into answers, and its discoveries into the foundation for something even greater. The first in line is the Nancy Grace Roman Space Telescope, scheduled to launch later this decade. Roman is not designed to probe individual planets as Webb does, but to survey the sky on a grand scale. Its wide-field vision will reveal thousands of new exoplanets through microlensing events where a foreground star magnifies a background one. Roman will also map dark energy with exquisite precision. For exoplanet science, it will provide the statistics, the broad context that Webb's deep but narrow view cannot. On the ground, a new generation of giant telescopes is rising. The extremely large telescope in Chile, with a mirror 39 meters across, will dwarf anything built before. Alongside it will stand the giant Magellan telescope and the 30-meter telescope. These instruments, with adaptive optics to sharpen their vision, will target some of the planets Webb identifies as promising. They will dissect their atmospheres in visible and near-infrared light, resolving details Webb cannot see. Together, space and ground will work in concert. Webb scouting giants confirming, but the boldest vision belongs to the Future Habitable Worlds Observatory, a mission still in planning but already shaping dreams. Its purpose is clear: to find and study true Earth-like planets. Unlike Webb, which is optimized for many cosmic questions, the Habitable Worlds Observatory will be designed with a singular focus: biosignatures. With coronagraphs or star shades to block the overwhelming glare of parent stars, it will be able to capture direct images of planets like our own. It will not just read their atmospheres in transit, but actually see their reflected light, perhaps even detecting surface features, oceans or seasonal changes. Webb is the bridge to this future. It proves the techniques, builds the catalogues, and identifies the candidates. Without Webb, the Habitable Worlds Observatory would fly blind. With Webb, it will fly with purpose, guided to the most likely places to find life. The synergy extends further. Missions like Ariel from the European Space Agency will conduct atmospheric surveys of hundreds of planets. Small specialized telescopes will hunt for transits around nearby stars. Each piece adds to the mosaic, making the search for life a truly global endeavor. For humanity, this means the next 2 decades may be the most transformative in the history of astronomy. We will not only know that planets exist, we will know their climates, their chemistry, and perhaps their habitability. And if even one shows unambiguous signs of biology, the discovery will change everything. Not just science, but our sense of place in the cosmos. Webb began the hunt, but it is the first chapter of a longer story, one that will stretch into the future, written by telescopes yet to fly and questions yet to be asked. Imagine the moment. A spectrum arrives from a distant world and the pattern is undeniable. Oxygen and methane coexisting in disequilibrium, water vapour glistening in the lines. Perhaps even other exotic compounds that on Earth are linked to biology. The data are checked, rechecked, debated, confirmed, and then the announcement: we are no longer alone. For science, it would be a revolution on par with Copernicus showing that Earth orbits the Sun, or Darwin revealing the story of evolution. Astrobiology, once a field built on theory, would suddenly have evidence. Every branch of science would engage. Biologists would ask how alien metabolisms function. Chemists would wonder what molecules support them. Astronomers would seek out similar worlds to test whether life is rare or common. Theories of planet formation, climate, and evolution would all need rewriting in the light of this discovery. Religion and philosophy too would feel the impact. For some traditions, confirmation of life elsewhere would affirm the vastness of creation. For others, it might challenge long-held views of humanity's uniqueness. Questions of meaning, purpose, and destiny would be reframed under a cosmic scale. Theologians and philosophers would debate whether intelligence and spirit are universal, or whether life is diverse but consciousness remains rare. For civilization, the effect could be unifying. National boundaries shrink when compared to the gulf of light years. The discovery would belong to no single nation but to all humanity. In a world often divided, the knowledge that life has blossomed elsewhere might remind us of our shared identity as Earthlings. It could inspire a new era of exploration, a renewed sense of purpose, a recognition that we are part of a greater community of the cosmos. Of course, uncertainty would remain. A biosignature is not a handshake. It would not tell us whether the life is microbial or multicellular, intelligent or simple. Yet even the humblest alien microbe would be enough to prove that biology is not unique to Earth. That would imply that life is a natural outcome of chemistry, not a miracle confined to one planet. And if life arises easily, then somewhere intelligence might too. The discovery would not end the search. It would ignite it. And yet we must prepare for the psychological weight of such a revelation. Some might fear it, imagining threats where none exist. Others might dismiss it, clinging to the belief that Earth is singular. But for many it would be awe, the sense that the universe has just grown larger, more alive, more mysterious than ever before. Webb may not be the telescope to deliver that ultimate proof, but it is paving the way, showing us where to look, teaching us how to read the skies. And if the day comes when a planet's spectrum declares beyond reasonable doubt that life breathes beneath alien suns, then Webb will have been the herald of that age. The search for life is no longer the domain of myth or speculation. It has become an experiment, careful, methodical, and breathtaking in scope. James Webb has given us the first tools to probe the skies of distant worlds, to read their atmospheres as if they were books written in light. What was once philosophy has become data. What was once imagination has become measurement, and yet the story is far from finished. Webb's spectra show us diversity, complexity, and mystery. Some worlds whisper of chemistry that hints at oceans. Others puzzle us with signals we cannot yet explain. The telescope has revealed more questions than answers, and in science that is the surest sign of progress. We now stand at a threshold. Ahead lies the promise of new telescopes, new missions, and new generations of explorers. Together they will build on Webb's foundation, mapping planets in detail. Perhaps one day capturing the reflection of alien oceans, the shimmer of unfamiliar clouds, or the faint pulse of life itself. But even if no definitive biosignature comes soon, the journey itself has meaning. It shows us that Earth is not alone in being a world of consequence. It reminds us that the universe is not a void but a tapestry of possibilities, and it forces us to confront the deeper question: if life is out there, what does that make of us? Perhaps we are rare, a singular spark in a vast dark. Or perhaps life is abundant and the galaxy is alive with voices waiting to be heard. Both possibilities are profound. One tells us how precious we are. The other tells us how connected we are. Either way, the universe becomes richer, larger, more alive. So the hunt continues. Webb watches in silence, capturing light that has travelled for centuries, waiting for us to decode its message. Each spectrum is a letter from the cosmos, and somewhere among them perhaps lies the word we long to read: life. Until then, we listen, we wonder, and we keep searching. Thank you for joining me on this journey. The universe is vast, the questions endless, and the adventure has only just begun.